Thank you. Thank you for giving me the opportunity to speak here. Judging from the list of participants, I had a quick look at it. I got the feeling that we have people from very mixed backgrounds here. In particular, I feel that the trade of geometric topologists is not overrepresented. So I guess that it may be a good idea to give a, well, more survey-ish talk, which tries to outline in broad strokes how the entire business of assembly maps and the isomorphism conjectures due to Farrell and Jones help us understand the topology of high-dimensional manifolds, which is basically the goal for my talk today. And it just so happens that all the theory that we have for understanding high-dimensional manifolds works particularly well if we try to apply it to aspherical manifolds, which is why I would like to speak about an arbitrary, for the beginning arbitrary, closed, connected, aspherical manifold of dimension at least 5 during this talk. So M will always denote this gadget, where by manifold I only mean topological manifold. And the first question that people cared about or studied intensively in surgery theory was the classification of manifolds. And now for spherical manifolds, there's a very prominent and long-standing conjecture, namely the Burrell Conjecture, which tells us that we expect these sort of manifolds to be topologically rigid in the following sense. The Burrell Conjecture states that given any such manifold, or given two such manifolds and a homotopy equivalence between them, the conjecture says this homotopy equivalence is in fact homotopic to a homeomorphism. So let me write that out. Any homotopy equivalence of closed aspherical topological manifolds is homotopic to a homeomorphism. In particular, the homeomorphism type of such a manifold is completely determined by its fundamental group. And the way people go about studying this conjecture, or one way to phrase this conjecture, is in the language employed by surgery theory. And in understanding or classifying high-dimensional manifolds, surgery theory studies something which is called the structure set. So let me define what that is. The structure set of a, now this could be any topological manifold, is the following. We look at homotopy equivalences from some other manifold to the given manifold. So N here now is again some closed manifold of the same dimension. And the correct way to approach this when I say homotopy equivalence here is to mod out the following equivalence relation. I identify two such things if they are H cobordant, in the sense that what I do, I have two such manifolds, N0 and N1, together with a specified homotopy equivalence to M. And then on the right-hand side, I can just take the trivial H cobordism over M, which is just a cylinder. And so I identify this with, or the two copies of M that I have with the two ends of the cylinder. And then I say I'd like to have some H cobordism here such that these maps extend to a homotopy equivalence to the cylinder. So it turns out that this is, in general, the correct equivalence relation to mod out. Now, the structure set that I've written down now doesn't seem to have such a direct relation to the Burrell conjecture, because okay, we're looking at homotopy equivalences of manifolds, but the relation that we mod out here has not exactly something to do with what we're saying in the Burrell conjecture. But the following is true. Suppose that we know for some reason that the whitehead group of the fundamental group of this manifold is trivial. So maybe as a quick reminder, we can form the whitehead group of any discrete group. This is just given as we consider K1 of the integral group ring. And then we mod out by, let me write this as plus minus G. So we mod out by the subgroup generated by the trivial units in K1. So think of K1 as the abelianization of the infinite general linear group over the integral group ring. Then these are invertible 1 times 1 matrices. They define a subgroup, and you mod out those, and that's by definition the whitehead group. If we assume that this guy is trivial, then we know that any homotopy equivalence is simple. In particular, all these are simple. And then there's another theorem of geometric topology, the S-cobordism theorem, which tells us that any H-cobordism over a manifold with such a fundamental group is in fact trivial, is in fact homeomorphic to a cylinder. So in this case, we know that W itself is homeomorphic to a cylinder relative to one of the components that may stay fixed. And if you then spend a minute on decoding what this actually means, it tells you that this H-cobordism relation simplifies to something which is much closer to what we're looking at in the Burrell conjecture. It tells us that the structure set of M is in fact given still by homotopy equivalences from some other manifold to M. But the relation that we mod out becomes the following. So we identify two homotopy equivalences with the same target M, if and only if there is a homeomorphism of the domain such that the resulting triangle commutes at least up to homotopy. And now you observe, since M is a manifold, this set has a preferred base point, namely the identity. And if the structure set now is a single point, then this tells us that any homotopy equivalence, so we can choose the identity for one of these homotopy equivalents, take any other homotopy equivalence for the second, and then this relation tells us precisely that any homotopy equivalence of such manifolds is homotopic to a homeomorphism. So in that way, we're able to rephrase the Burrell conjecture in the language of surgery theory. And the reason why I'm doing that is, of course, that surgery theory has a lot to say about this structure set. And this is a pretty long story, which I don't want to delve into. So people started studying the structure set first for simply connected manifolds. This goes back to Browder. Then they generalized it to manifolds with fundamental group, which is the big contribution by C.T.C. Wald, doing surgery theory in the presence of a non-trivial fundamental group. And there are contributions by other people like Novikov and Sullivan. And what comes out, or what came out in the end, was that this structure set actually fits into a long exact sequence, which helps us computing the structure set if we understand the other terms and the maps appearing there. I don't want to discuss the surgery exact sequence here, but then Quinn also came along and noticed that you can obtain this long exact sequence that people have been studying in surgery theory as the induced sequence of homotopy groups of a fibration or homotopy fibration sequence of spaces, where this structure set becomes pi 0 of some space. And finally, after many more years, Ranitsky developed his algebraic theory of surgery, which allowed him to phrase all of this, in the case of topological manifolds, in terms of L theory. And in particular, what comes out at the end, and this is now mainly due to Ranitsky in this form, is that this structure set for a topological manifold is actually not only a pointed set, but it's even an abelian group, because in fact it arises as pi 0 of a certain structure spectrum, which can be defined in terms of L theory. And moreover, this structure spectrum, which is, whose homotopy groups are known to sit in a long exact sequence, actually arises as the homotopy fiber of a certain map. And this relation is precisely the relation that gives us this long exact sequence that people have been studying before. So moreover, this structure set can be identified with the homotopy fiber of a certain map, which I'd like to call alpha LM, and which I'm going to explain next. So if the transition was somewhat obscure, this is the important thing to take away, so that we can identify the structure set as pi 0 of a certain structure spectrum associated to M, and this structure spectrum arises as the homotopy fiber of a certain map, which I'm going to explain now. This map alpha is what people call an assembly map. And in this particular case, it goes like this. We can consider a functor, L theory, which is a certain invariant associated to quadratic forms, if you like. But we interpret this as a functor from spaces to spectra, simply by saying, well, if I have a space X, then what I do is the following. I take its fundamental group, I take the integral group ring, then I have a ring, and it makes sense to speak about L theory of this ring. Now I'm going to put this into quotation marks, because you will, of course, immediately explain that this is not a functor, but there are ways to get rid of the problems arising from X maybe having several components and the lack of base points, so that's not a real trouble. This is morally what this functor is supposed to do. And now by definition, we observe that this functor is homotopy invariant, because the very first construction that we did was the homotopy invariant construction. And now, one way you can think about assembly is you may ask the question, to which extent is this functor built up from local data, assembled from local data? And by local data, I mean, to which extent can we compute this functor as the evaluation of some homology theory? And in fact, there's a universal way of approximating this functor by a homology theory, which goes as follows. So let's fix some space X, and then we can look at L of X, which was now by definition L theory of the integral group ring of this gadget. And now we can do the following. So one possible description of this universal approximation goes as follows. Consider the singular set of X, so the set of all singular simplices of X. Those are maps from some standard P simplex into X. And what we can do is we can evaluate our functor L just on the standard simplex. And since this is associated to a certain singular simplex, we get a natural map from the L theory of this delta P to the L theory of X. And all these are compatible with respect to the phase inclusions that you have among the singular simplices. So that allows you to take the homotopy co-limit over this diagram. And now you observe that since L is a homotopy invariant functor, this diagram of which you're taking the homotopy co-limit is essentially constant. So that tells you that this homotopy co-limit can actually be identified with something like the realization of the singular set of X at a base point and smash with the L theory of a point. And of course, this is again weakly equivalent to X. It's just some CW approximation to X. So what we now have here on the left side is we have some space at a base point smashed with a spectrum. That's a homology theory. And we have a transformation from this homology theory into our functor evaluated on the space that we're actually interested in. And this is what's called the assembly map. So this is now the L-theoretic assembly map associated to X. And Ranitzky's theorem tells us that if X is a closed topological manifold, then we can identify this structure spectrum precisely with this homotopy fiber of this assembly map. So the corollary that we can derive from this is the following. We were originally asking, when we're thinking about the Burrell conjecture, is pi 0 of this structure spectrum trivial? And now we have identified this structure spectrum as the homotopy fiber of this map. So one sufficient condition that ensures that the structure set is a point would of course be to say, well, this assembly map is an equivalence. And let me just write this down as an observation to fix that on the blackboard. So if alpha LM, or let's say alpha B pi, note that an aspherical manifold is just a model for B pi of some discrete group pi. So if alpha B pi is an equivalence, and the whitehead group of pi is trivial, then the discussion up to this point tells us that the Burrell conjecture does in fact hold for manifolds with fundamental group pi. So this is now one way to approach this conjecture, and I wouldn't be telling you about this if it wasn't a feasible way of approaching this conjecture, which is what the next theorem is supposed to tell you. So suppose pi is torsion-free. Of course, this assumption is harmless if we're thinking about this question, because if we have an aspherical manifold, then its fundamental group is necessarily torsion-free. So if pi is torsion-free, then we know that alpha L B pi is an equivalence, for example, for the following groups. We know that it is an equivalence for hyperbolic groups in the sense of Gromov. Or let me also immediately add and cat 0 groups. So these are groups acting co-compactly properly on a finite dimensional cat 0 space, where cat 0 spaces are certain metric spaces which have non-positive curvature properties. If you don't know the term, don't worry about it. And this is due to Bartels and Lück. And moreover, it is also an equivalence for polycyclic groups, which was proven by Bartels, Farrell and Lück. And I don't want to go into this. There are all sorts of inheritance properties for these assembly maps to be an equivalence, which allow you to generalize this to create bigger and bigger classes of groups. But this is not really what my talk is about. So there are at least two, well, significant classes of groups for which we know that this alpha L, this assembly map in L theory, is an equivalence. Now, of course, this doesn't yet quite answer our question about the Burrell conjecture, because in our observation, we also had to assume that the whitehead group is trivial. So one additional piece of information that is missing is knowledge about the Whitehead group. And fortunately enough, there's another assembly map which allows us to approach this question. So it hopefully doesn't really come as a surprise, since the Whitehead group was defined in terms of algebraic K-theory, that we will now consider an assembly map in algebraic K-theory. So similar to the functor L that I outlined before, we have another functor K from spaces to spectra, which takes a space X and maps it, to the K-theory of its integral group ring, with the same caveat as before, that you have to pay a little more attention to actually turn this into a functor. And then by the same procedure, we obtain an assembly map, alpha K X, which goes from, well, let me just say, X plus smash. So K of a point will now just be the K-theory of the integers, and maps to the K-theory of Z pi 1x. Now something that is not that difficult to figure out, but which I will just state as a fact, is if we again look at the assembly map where we plug in the classifying space of a discrete group for X, then this assembly map allows us to describe the Whitehead group, because it turns out that the Whitehead group of a discrete group is isomorphic to the co-kernel of the assembly map in degree 1. So again, in this case it tells us if we know that the K-theoretic assembly map in degree 1 is surjective, then the Whitehead group of that discrete group that we are looking at is trivial. So in particular, if we know that the K-theoretic assembly map is an equivalence, then this is definitely sufficient to deduce that the Whitehead group of that group vanishes. And here's another theorem which is somewhat similar to the one up there, but yet sufficiently different that I should write it down. Suppose again that pi is torsion free. Then the following is true. So then we know that alpha K B pi is an equivalence for certain classes of groups. This time we have again the hyperbolic groups, which was shown by Bartels, Lück and Reich. Then again we have those cat 0 groups, which was done by Bartels and Lück. And Wegner. We also have the polycyclic groups, which is again due to Bartels, Farrell and Lück. And finally, here, so the class of polycyclic groups is actually not or properly contained in the next one. We even know it for solvable groups. And special cases were proven in this class by Farrell and Wu, and then the general case of solvable groups was obtained by Wegner. So in particular, if we look, say, at hyperbolic groups or polycyclic groups, then we know that both of our assumptions of this observation are satisfied. So both the Whitehead group vanishes and the L-theoretic assembly map is an equivalence. So for these manifolds, for spherical manifolds with such fundamental groups, we know that the Burrell conjecture is in fact true. So that's as much as I wanted to say about the classification question. And now we have obtained a classification result, a certain uniqueness result for such manifolds. And it might be your natural instinct to ask the next level question, what about automorphisms of these guys? And that's what we're going to do now. Any questions while I'm cleaning the blackboard? Automorphisms it is then. So the first thing that one has to worry about is what is actually the question that one would like to answer when we want to speak about automorphisms of manifolds. And what I would like to do is to say, take such a high-dimensional spherical closed manifold, take its topological group of homeomorphisms, and now I would like to ask the question, what are the homotopy groups of this gadget? So in particular, if I look at the pi0 part of that statement, I'm asking how many automorphisms of such a closed spherical manifold are there up to isotopy? So what we would like to consider is the group top M. And when I'm asking about homotopy groups, it is of course sufficient to study only the weak homotopy type of this space, which is why I will adopt the convention that when I say top of M, I don't precisely mean the topological group of self-homeomorphisms, but what I do, I take the singular set of this guy and realize that. So I take a functorial CW approximation. This will be useful in a moment. And in trying to study now this group, you may of course first of all try to compare this to other gadgets that are maybe easier to understand. And one thing that we can definitely do is we might feel inclined to compare the group of self-homeomorphisms just to the monoid of self-homotopy equivalences, which is maybe something that's more easy to understand. And since any homeomorphism is a homotopy equivalence, we definitely have a map. So by G of M, I will denote the topological monoid, or approximation to the topological monoid of self-homotopy equivalences of M. And now, it is in fact not so difficult to compute that if you look at the homotopy groups of G of M, or let me phrase this differently. If you take G of B pi, where B pi is just the classifying space of some discrete group, then you can compute these homotopy groups, and they turn out to be the outer automorphisms of your group in degree 0, the center of your group in degree 1, and they are trivial in all other degrees. So it looks a bit like we're not really able to get much information out of this, but it's probably more interesting to look at the homotopy fiber or co-fiber of this map if we want to really get much information about top of M. And now, by stroke of luck, there is a way how we can still use this information combined with what we were discussing before to actually get information about top of M. And now the next definition is maybe not the most intuitive one, so let me just make it. It's a good idea to do this. You can compare top M to the group of block homeomorphisms of M. Now what is this? I define top M to be the realization of the singular set of the group of homeomorphisms of M. So what does that mean? A typical simplex in this space looks like so let me write this maybe here. What's a typical simplex in here? So this looks like a homeomorphism of M times delta P to M times delta P such that this homeomorphism is compatible with the projection onto the simplex coordinate. That's just by adjunction. And now a block homeomorphism is not quite as strict a homeomorphism or an automorphism of M times delta P as this one, but we only require that it preserves all the faces of the simplex. That's still enough to get at least a semi-simplicial structure, and that's by definition the group of block homeomorphisms. So typical simplex here is again an automorphism of M cross delta P, but only compatible with face inclusions. And there's a similar gadget for self-homotopy equivalences, where we say we only look at self-homotopy equivalences which preserve faces, and that's called the group of, or the monoid of block self-homotopy equivalences. And similarly, we have an inclusion here. And now it turns out that actually, if you only look at homotopy equivalences, the definitions don't make a difference. These guys have the same homotopy type. You can just do a certain linear homotopy to produce out of such a block homotopy equivalence an honest homotopy equivalence. So we haven't changed really much here. But now, this comparison map is in fact rather interesting, and I should get rid of the line that I drew here. For the following reason. So, we may now try to compare these two gadgets, the monoid of block homotopy equivalences and the block homeomorphisms. And those sit in a homotopy fiber sequence, where I have down here something called G twiddle of M mod top twiddle of M. And there are different ways to think about this. So one definition would be for this guy, take the classifying spaces of both of these guys, so de-loop this map once and then take the homotopy fiber.
So you haven't discussed whether these are all connected spectra or not. You're verging on that right now.
So those are in fact only spaces. And they are not infinite loop spaces.
But there's a pi minus 1 issue here. Pi 0 of top to pi 0 of G to what?
To pi 0 of this homotopy fiber. So this I define as the homotopy fiber of B top twiddle M to BG twiddle M. And I think that this is also the usual convention how people define this space. And now comes the stroke of luck that I was alluding to, because this homotopy fiber is in fact related to gadgets that we were already talking about. So this homotopy fiber G twiddle of M mod top twiddle of M is, well, at least equivalent to a collection of components of, let's say, the infinite loop space associated to the structure space or structure spectrum of our manifold M. So G of M is equivalent to a collection of components of, now let me say, loops infinity of, whoops, the structure spectrum of M, assuming that the Whitehead group is trivial. And now this is really fortunate in the setting that we are in, because we have a list of examples where we know that both the Whitehead group is trivial and we know that this spectrum is in fact trivial. So that tells us that the difference between top twiddle and G twiddle is also trivial. So in those cases we know that this map is in fact an equivalence, and so we have computed the homotopy groups of top twiddle as the homotopy groups of G of M, which look very simple. So that tells us that in trying to compute the homotopy groups of top M, a good idea is to focus our attention on the difference between top and block top, which is, by a similar or analogous definition, a certain space top twiddle mod top, which is defined as the homotopy fiber of the D loop of this map. Unfortunately, there's a theorem due to Weiss and Williams which puts us in a position that allows us to connect the homotopy groups of this space again back up to algebraic K-theory. And the theorem goes as follows. So Weiss-Williams construct a map which starts in this space, top twiddle M, mod top M, and maps to something that I need to define. So the target of this map will be defined in terms, again, of a certain assembly map, but it's none of the two that we already had, but there's yet another assembly map that we need to study. There's a functor A from spaces to spectra, which is originally due to Waldhausen. which you can think of as doing the following. Take a space X, and now take the loop group of X, take its spherical group ring, and then apply algebraic K-theory. So this is now not the K-theory of a traditional discrete ring, but it's the K-theory of a certain associative ring spectrum. And basically, as before, we have to put in a bit of thought in saying precisely what this is supposed to mean, but I don't want to go into the technical intricacies of defining this properly. So this is what's maybe again morally here, the K-theory of the group ring, which is the spherical group ring of loops X. Note that if X is in fact a classifying space, we can just take the spherical group ring of the fundamental group of that classifying space. And now associated to this functor, we have an a-theoretic assembly map which goes from B pi plus mesh A of a point to A of B pi. Or actually, wow, that was a bad idea. I should really state this for any space. And now what we have here on the right-hand side is in fact the homotopy fiber of this assembly map. And let's consider it a part of the theorem that this homotopy fiber carries a certain action by the cyclic group of order 2. And once we accept that such an action exists, we can take the homotopy orbit spectrum of this C2 action and then take the associated infinite loop space. And the claim about this map is that we can describe its connectivity in terms of a certain invariant associated to manifolds, which for a topological manifold is not really known at the moment. But if we assume that our manifold is smoothable, so there, such that, I put this as a parenthesis, this is for smoothable manifolds. We know that the connectivity of this map diverges as the dimension becomes larger. So what this is supposed to mean is that for smoothable manifolds, there is a certain lower bound on the connectivity of this map, which is given in terms of the dimension of our manifold. It's roughly n over 3, I think. And that tells us that the higher dimensional our manifold is, the higher the connectivity of this map is. And this last part of the theorem, so really knowing explicit bounds for this connectivity, this is due to Igusa. But now this tells us that if our manifold is sufficiently high dimensional, then at least in a range of degrees, we can compute the difference between top and top twiddle in terms of the homotopy fiber of this a-theoretic assembly map. Now, of course, the situation becomes, or may become a bit more difficult here, as in the first step, you may hope that, again, we can show that the a-theoretic assembly map is an equivalence, and then we know this is 0, and then a lot of degrees we have 0 here, and there's more or less nothing left as at least the homotopy groups of top of M in a certain range of degrees. But it turns out that this is definitely not the case, and you need a refined version of the assembly map in order to really get a statement here, in order to compute this homotopy fiber. And that goes as follows. So recall again, M wasn't a spherical manifold, so we were actually looking at a B pi here. And let's give another characterization or another description of this assembly map. So we are at the moment looking at the assembly map from B pi plus mesh A of a point to A of B pi. we're going to switch perspectives a little bit insofar as we will consider now A as a functor on a slightly different category than spaces. Actually, we can get this by precomposing with another functor. But say we consider A as a functor from the orbit category of pi to spectra, which works in such a way that if we have a transitive pi set here, pi mod h, then we map that to the A theory of BH. Again, one has to be wary about functoriality issues, but let's not worry about that. And if we think about it, if we think about it this way, then we might say that this is the homotopy colimit of a constant functor with value a of a point on the diagram, which considers pi just as a groupoid. Or instead of saying I consider the group pi as a groupoid, I can think about this as the homotopy colimit of the diagram with value a of a point taken over the orbit category of pi, where I restrict to the full subcategory spanned by pi mod 1. Now, if I think about the assembly map in this way, then it looks like an induction statement. So if you think about a very classical situation, say pi was finite and we had a Mackey functor and we forget about the Ho here, then this would tell us something like our functor is induced from the trivial subgroup. And the claim now is A theory is not induced from the trivial subgroup, but possibly from a larger collection of subgroups. And now the question would be, what is the correct collection of subgroups from which this functor is induced? And that's precisely what the Farrell-Jones conjecture tells us, or predicts. So the prediction that the Farrell-Jones conjecture makes is that this functor that we are considering is not induced from the trivial subgroup, but it is induced from the family of virtually cyclic subgroups. Where a virtually cyclic subgroup is a group which contains a cyclic subgroup of finite index. So this is, of course, only an interesting definition for if you have an infinite cyclic subgroup, otherwise your group is just finite. And now this conjecture can be phrased not only for A theory, but for all of the three functors that we have been considering already for the K theory of group rings, the L theory of group rings, and the K theory of spherical group rings, also known as A theory. And let me also add at this point that if you take this formulation, is there a question?
No.
Okay, sorry. If you look at this assembly map now, which the Farrell-Jones conjecture predicts to be, oh, I should maybe put a conjecture somewhere. So this is an equivalence for all pi. So if you phrase it this way, then we can remove the assumption that our group is torsion-free in the theorems that I had on the blackboard before about the K-theoretic and the L-theoretic assembly map. And you can also use different coefficients rings than just the integers. You can take any associative ring that you would like.
But in the case of K and M, if the group is torsion-free, it makes no difference whether you put the sig or you put the point. Why is it different for A?
For A, it's different because, for example, the nil terms of the sphere spectrum are non-trivial. That's going to pop up at the end of my talk as well. Yeah, it's the coefficient ring there that makes additional trouble. Okay, so in fact, if you look at this assembly map, then the theorems we had before are also true for groups with torsion and for more general coefficient rings. And now let me come to the final theorem of my talk, which now contains a probably familiar looking list of groups. So this, maybe this map should get a name. Let me call this the Farrell-Jones assembly map associated to the functor f. So now I can say that the atheoretic assembly map in the Farrell-Jones sense is an equivalence for polycyclic groups. This was proved by Mark Ullmann and myself. It's also true for these more geometrically flavored groups like hyperbolic and cat-zero groups, which was established by Niels Edwin Enkelmann, Wolfgang Lück, Malte Pieper, Ullmann, and myself. And finally, we also know that it's true for, well, let me just say, solvable groups. So this was done by Daniel Kasprowski, Ullmann, Wegner, myself, and also independently by Farrell and Wu. And again, there's a number of inheritance properties that allows you to deduce this sort of theorem for more groups than just these that are on the blackboard. So now, since we know that this is an equivalence, this gives us some means of trying to compute the homotopy fiber that we have up there on the blackboard. Of course, the question how well we're actually able to compute this homotopy fiber depends a lot on the group and how complicated this homotopy colimit becomes. But there are at least some cases in which the situation is easy enough so that we can say something. And let me close my talk by giving one quick example. I'm coming to that. So let's take the example where the fundamental group is hyperbolic. And let's also assume that our manifold is smoothable, because then we know that if the dimension of our manifold is at least 10, then 0 is in the connectivity range of the map I have just erased. And for a hyperbolic group, we are in a fairly nice situation because we have to compute this homotopy colimit up there. Now, we have a torsion-free hyperbolic group, and for these, it is known that if we have, so virtually cyclic subgroups in this group is simply a cyclic group because there's no torsion, and if we have a non-trivial cyclic group, subgroup of this group, then it's known that each of these is contained in a maximal infinite cyclic subgroup, and each of these maximal infinite cyclic subgroups has a trivial Weil group. So that tells us that this homotopy colimit up there is really, really simple, because if we look at the homotopy fiber, then, or I should say, first of all, that the same formula, if it holds for A theory, also holds for the homotopy fiber of the assembly map. And then evaluated on the trivial group, there's just nothing, because for a trivial group, the assembly map is an equivalence. So we only need to evaluate for each maximal infinite cyclic subgroup what we have. And what we get for this homotopy fiber is just a huge sum indexed over conjugacy classes of maximal infinite cyclic subgroups of our fundamental group. And for each of these, we get a copy of, now how do I want to call this? What's the best name for that? Okay. We get a copy of the homotopy fiber of the A-theoretic assembly map of the classifying space of C. Now note that this is just an S1. But what we have to do is we have to take the C2 homotopy orbits and then apply pi 0. Now what we know from the homotopy fiber sequence that we have, this also uses that the center of of this fundamental group is trivial, is that we get a short exact sequence for pi 0 top M, which projects onto the outer automorphisms of the fundamental group. And now the one thing left to do is compute this term. And unfortunately, at the moment, I'm unable to say what precisely this C2 action does. So this term can be described a little bit more explicitly. This decomposes into a sum of two equivalent spectra. One thing that you might hope is that maybe the C2 action just flips these two summands, so you have an induced spectrum, and then you know what you have here, but I'm unable to say that this is actually true at the moment. Nevertheless, there are computations about the homotopy groups of this homotopy fiber due to Lars Hesselholt, which tell us that, for example, one group that definitely contributes here is infinitely generated. It's a countable direct sum of Z mod 2s. So we're definitely expecting a big contribution to pi 0 of top M here, but at this point in time I'm unable to say what it precisely is. And yeah, I think that's all I wanted to say.
So, are there any questions? Chuck?
Can you tell us for what groups do we actually know the Burrell conjecture at this point?
The Burrell conjecture, so definitely all we had on the blackboard. We also know it for lattices in almost connected Lie groups. And so I was always alluding to these.
So it's true for all of the groups that you've been talking about?
Yes.
A little hard to trace through your...
Oh, I'm sorry about that. Yes, so the groups that were on the blackboard, we know the Burrell conjecture for those.
So could it be that the C2 action makes this small again in principle, or is that already ruled out by what you...
So I would think that since the contribution that we have there, if they are non-trivial, they are not even finally generated, I'm expecting that we will definitely have a big contribution there.